All right, we're going to start on 5.2, which is the addition rule and complements. Okay, so I want to first talk about the term mutually exclusive, or another term for that is disjoint. Okay, and that means they share nothing in common. Okay, so if I were to draw a Venn diagram, okay, if this is event A, this is event B, they don't overlap at all, they share nothing in common, okay? So we're going to talk about the addition rule for disjoint events, okay? So that's the probability of E or F equals the probability of E plus the probability of F. Now, I do actually have something to share, although this isn't that big of a deal, but if you want to go ahead and open up your Canvas for a second, I've got a little probability model here. Oh, and then of course this is going to make me log in. Oh, and then I get that stupid screen every time. All right, so go to Math 2040, go to Assignments, and we're going to go down here to the in-class worksheets. And which worksheet is this? This is 5.2. Okay. So, so some background on this data set. Basically, our number system contains 10 digits, 0 through 9. A lot of people forget to count the 0, even on the quiz today. Don't forget the 0. So there was a physicist named Frank Benford in 1938, as well as apparently Simon Newcomb did this back in 1891, and he discovered that when you're talking about the first digit of a number, you usually don't, oh, and I don't think I'm sharing this. You usually don't write, here, before I share that, I'm going to say, you don't write 0, 1, 2. Usually you'd write that as 12. So 0 is usually not the first number in a thing. So one of the things that Frank Benford discovered was, okay, so the number 1 appears about 30% of the time, the number 2 is 17% of the time, etc. And so 9 is least likely to happen. So they're not equally likely. So the first question I have is, how would you verify that this is a legitimate probability model? Okay, what rules? 0 and 1. Okay, so are all of these values here between 0 and 1? I'll highlight it that way. All of those between 0 and 1? Okay, so pass the first rule, check. They should all add up to 1. Okay, so if I enable editing here, let's see. If I put it there, add that up, adds up to 1. Okay, so it passed the 2 rules. Perfect. Sounds like a good test question. Okay, keep that one in the back of your mind. All right, what's the probability that the first digit is a 1 or a 2? How would you figure that out, David? How would you figure out the probability that the first digit is a 1 or a 2? You don't know? How about the addition rule for disjoint events? Can you be a 1 or a 2 at the same time? No, so therefore they're disjoint, right? So when you see the word or, you think Addition. So what am I adding? David? You're adding the previous one? I only want the ones and the twos. So equals, what's the probability of a 1? You don't know? It's right there, staring you in the face. 0.301. And then I'm going to add the probability of 2, which is, probability of a 2 is 0. 0.176. Okay, this is just a relative frequency distribution table. Okay, so I'm going to add those two together. Okay, so you've got almost a 50% chance, 0.477. Now remember, when we leave these, I don't care if you say that they're percentages, but leave them as decimals. So but the probability that the first digit is a 1 or a 2 is 0.477. Now that you've figured that out, can you tell me the probability that the first digit is at least a 6? I'm trying to make sure David's learning here. So if it's at least a 6, what's the probability of the 6? 6, 7, okay, plus what? At least a 6. All of them. Yeah, I could add them all up just like this. Okay, which is 0.222. How did I do what? Well, there's a couple different ways you could do it. Here, I'll do it again. So I just went 6 plus 7 plus 8 plus 9, just like that. Or if I like to use the sum command, equals sum, and I can just highlight them all with my mouse, and I'll still get the same answer. Okay? Does that make sense? You can ace my test quiz tomorrow? Almost test tomorrow, huh? Test is in 2 days. Okay? All right, so now, let's see. So I'm not going to pick on Austin because it was Colton told me you're not a card player.
What's that?
You're not a card player?
No.
Are you not 21 yet?
No, I am.
You are, and you don't go to Vegas all the time?
No, not yet.
Oh man, I thought that was like a rite of passage, wasn't it? 21, you go to Vegas.
Yeah.
My brother, he used to get so excited. He's like, when he turned 21, he's like, I can't wait to show my ID. So anyway, what's the probability? Let's talk about who are my card players. Sean, are you a card player? Oh, good. Was that why you were raising your hand? No? What was your question? So yeah, so actually I'll back up a little bit since you asked about Benford's law. So this is actually used for, the IRS uses this to find out if somebody is faking their taxes, because they know that the first digit should follow this, and so if they've got too many, 9s on there, for example, they'll be like, ooh, there's a good chance this person's faking it. Okay, so it's a way to detect fraud. So anyway, that's kind of interesting. If you're faking your taxes, make sure you're following Benford's law, which is probably more work than just doing it right. Okay? All right, so going back to the cards, what's the probability that I draw a king? There's going to be some card problems on here, by the way. So I'm going to expect everybody to know. So do you want to know really quickly? There's 52 cards in a deck. You got 4 kings, queens, jacks, 10s, all the way down to 2s. Also, you have an ace. 4 of everything. 4 of everything. So the way it works is you've got a king of hearts. You've got a king of diamonds. That's not a very good diamond. Diamonds. You got a king of clubs, and you got a king of spades. Close enough. Okay? So that's what you've got, one of every suit. They refer to these as a suit. Okay? You got your hearts, clubs, diamonds, and Spades. Anyway. So, probability that you draw a king out of a deck of cards, Sean? 4 out of 52. I'm fine with that, or if you simplified that, that would be 1 out of 13. Okay? What would be the probability that you would draw a king or a queen? 2 out of 13. So you could do, because there's 4 kings, right? Plus 4 queens, which is 8 out of 52, which is the same thing as 2 out of 13. Okay? How about the probability that you draw a king, a queen, or a jack on the first pick? So, whose turn is it? It's got to be Tanner's turn. $12 out of 52. Yep, there's 4 of everything, so 12 out of 52, which works out to be 3 out of 13. Okay? Now, here's a trick question for you. What's the probability of drawing a king or a diamond? Diamond. Now, let's think about this. I've got 4 kings, right? And I've also got a boatload of diamonds. And what do you notice that I've circled there? I circled the diamond twice, right? The king of diamonds twice. So, are the kings and the diamonds, are those disjoint? No. So, let's talk about the addition rule. When not disjoint. Okay? The probability of E or F equals the probability of E plus the probability of F minus the probability of E and F. Okay? So you really need to pay very close attention to and versus or. Okay? In fact, we'll talk about ands more in a minute, but at any rate, as I go back here, if I'm doing the king or the diamond, okay, so I'm going to pick on, oh, I know your last name is Bracco. I can't remember your first name. Janessa. I knew it wasn't Jenna. I knew it was close, though. Janessa, what's the probability of drawing a king out of a deck of cards? 4 out of 52. What's the probability of drawing a diamond out of a deck of cards? 13 out of 52. Because there's an or, we're going to add them, but these are no longer disjoint. Basically, I've circled that diamond twice, right? And so, therefore, I get to subtract this one that I've double counted, right? Which is 1 out of 52. So you're going to find, even though you could have simplified these, you probably don't want to simplify this one because you're going to have to get a common denominator anyway. So 4 plus 13 is 17 minus 1 is 16 out of 52, which is the same thing as 8 out of 26, which is 4 out of 13. Okay? All right, how about this one? The probability that I draw a 2, a 3, or a spade. Okay, so I'm going to pick on, I know Tyler's name. I want to say it's Matthew. Oh, I got it right. What's the probability of drawing a 2 out of a deck of cards? plus 4 out of 52, plus 13 out of 52, minus 2 out of 52. Very well done. So we've got 4 2s, 4 3s, 13 spades, but now we've got a 2 of spades and we've got a 3 of spades, so we got to subtract off both of those. 4 plus 4 is plus 13. 21 minus 2, 19 out of 52. That actually doesn't even simplify. Okay? Piece of cake? All right. No, but
And do you always want us to simplify on like equation? Also, like would it be fair to put 16 out of 52, or do you always want us to put 4 out of 13? Doesn't matter.
I'll take either answer. You could put either 16 out of 52 or 4 out of 13. I'll be fine with that. In fact, I would rather you left it as a fraction like that than as a decimal. Okay. All right. Let's talk about the complement rule. Okay. So the probability of E, and I'm going to put a C complement, equals 1 minus the probability of event E. Okay? So let me ask you this. What's the probability that I do not draw a 2, a 3, or a spade? It must be McKenna's turn. Or is it Mackenzie? Mackenzie, sorry. Very good. 1 minus 19 over 52. Let's see, that's 50, here, I do it this way. 52 over 52 minus 19 over 52. Let's see, 20 would be 32, so 33 out of 52. Okay? So a lot of times the complement rule is easier to figure out. Oh, I didn't know. No. Was I doing this right? No, I didn't. I wasn't recording any of that. Okay, anyway, there you go. Now you can see the board. Here, I'll put that there for a minute. For those of you who aren't here, okay, you should come. All right. All right, let's talk a little bit about two-way tables. Let's go back to this spreadsheet that I had. And we'll talk a little bit about two-way tables. Okay? Okay, so they call this a two-way table. So this comes from the Census Bureau for adults 18 and over. Compute the probability that somebody is male. So I'm going to pick on Chris, since you can definitely see up close here. How would you figure the probability that somebody is male given this information? We need the total of everybody, right? So, in fact, let's just find all of our totals here. Okay, so if I sum that, and I sum that, and then I sum that, now I got everything, right? Okay, so Chris, probability that somebody is male would be 106.2 divided by what? 219.7, which works out to be 0.483. So about 48% of people in the census are male, according to this. What would be the probability that someone would be widowed? It must be, whose turn? How about Jonathan?
Would be the widow.
The widow, so we'd have to get this row total here, right? In fact, should we just do them all while we're at it? Let's do them all, because we'll probably need them. Okay, so the probability somebody is widowed is 183. Where are you seeing that? The widowed, I've got 13.9. Are you seeing something different? Okay, so 13.9 divided by 219.7. So about 6% of people are widowed. What would be the probability that someone is widowed or divorced? So I'm going to add, use parentheses here, the widowed plus the divorced close my parenthesis, and divide by my total. Now let's pick on somebody else, like, how about this, Tyler? How about probability that someone is male or widowed? Plus the 106.2 minus the what? 2.6, because those are not disjoint anymore, so we're using that. And we're going to divide by 219.7. So 0.534, you're either male or you're widowed. Okay? So we just use all of the addition rules and the when it's disjoint and not disjoint. So that last one was not disjoint. What were the what?
What were the, so you did the total of the males.
Yeah, we did the total of the males. Total of the males, which was 106, plus the total of the widows, which was 13.9, minus what I double counted, which was the 2.6. Close my parenthesis, divide by my grand total. Okay? Alrighty, well that was pretty easy. Okay, so real easy question for you. I'm going to pick on Austin. If 52% of the Americans play the lottery, how many don't play? 48%, that was easy. Compliment rule right there. All right, so that's the end of 5.2. Let's move on to 5.3, which is the independence rule. I'll stop sharing again here. All right, so 5.3, which is independence and the multiplication rule. Okay, so independence means the occurrence of event E does not affect event F. So what do you think dependence means? Yeah. E affects F. Okay, so let's think about this for a minute. I flip a coin, I get head. I flip a coin the second time, I'm picking on Franco. Is it going to be more or less likely, or just as likely as the first head? Just as likely. So is that an example of independence or dependence? That would be an example of what? Independence. That's correct. Okay, how about this one? Here's the event is earns a bachelor's degree. That's event E. The event is makes $100,000 a year. Are those two events independent or dependent? It could be independent. So let me ask you guys a question. Why are you guys in school? Huh? Because you want to get a better job because you want to make more money, right? So you think that the amount of money you make depends on your education, right? So would those be, let's talk about that again. So earns $100,000 or versus earns a bachelor's degree, are those events independent or dependent?
I would say in the majority of cases it would be dependent, but
there you go. There are outliers like Bill Gates, right? He didn't finish college. Okay, but as a general rule, you're all here because you want to make more money, right? So you're depending on the fact that your degree is going to help you make more money. It's going to make you more likely to get that, okay? How about this one? I've got two 24-year-old males. I'm going to pick them at random. Is the event male number 1 gets in a car accident, male number 2 gets in a car accident? Are those independent or dependent? Depends on whether they run into each other, right? As a general rule, if you took somebody from Utah, somebody from Georgia, would you think that those events would be independent or dependent? Probably independent. All right, so let's talk about the multiplication rule. Multiplication rule for independent events. Okay, now this is the probability of E and F. Okay, remember just a few minutes ago we were talking about ors. Now I'm talking about ands. The probability of E and F equals the probability of E times the probability of F. Okay, so compute the probability that they get a head and a head. Okay, so I'm going to pick on Kyle. What's the probability of a head on the first toss? 50% or 1/2, right? What's the probability of a head on the second toss? 50 or 1/2. Keep those as fractions. Okay. I've got an and here, a head on the first try and a head on the second try. So therefore, do I add or multiply them? No, I'm doing the multiplication rule here. I'm going to multiply them. So 1/2 times 1/2 equals 1/4. Okay? All right. Now, let's do this one. What if I tell you that the probability that a 24-year-old male survives the year is 0.9986? Okay? So you work for a life insurance company, you're trying to decide whether you want to insure this guy. What's the probability that 3 24-year-olds survive the year? Okay, we're assuming these are 3 independent males. How would you figure that out? It must be whose turn? Ramiro, it must be your turn. What's the probability that the first male survives the year? Yeah, probably the first male survives. 0.9986. What's the probability the second male survives? 0.9986. What's the probability the third male survives the year? 0.9986. What do I do with these numbers? Multiply them. Boom, boom. That gives me the answer 0.9958. Okay. How about this one? What's the probability that 20 24-year-old survives? Eric, it must be your turn.
0.9986.
0.9986 to the power of 20, which equals 0.9724. Okay? So this is just the multiplication rule. What if I asked you, turn this just a little bit, okay? What's the probability that at least 1 of 1,000 males die? Okay, how would you figure that out? I'd pick on Alex, but he's too far away and can't see. How about Ashley? You can see. You'd have to figure out the probability of at least 1. We did that one with David, right? So we had to do the 1 and the 2 and the 3 all the way up to the 1,000, right? Do you want to do that for me? We've only got 1 minute left. Is there an easier way to do that? David?
What
Well, so at least, anytime you see at least, you got to do the probability of 1 plus the probability of 2 plus the probability of 3, etc., all the way to the probability of 1,000. Which means I've got 1,000 calculations. There's got to be an easier way, right? What do you think, Chuck? Complement rule. Okay. How could I do this with the complement rule?
So since you've already got 0.9986, the extra 14 of that, make 1,000.
Okay. So you're kind of on the right track. Let's rewrite this. Instead of the probability that at least 1 of 1,000 die, let me make sure I did that. Yeah. It's the same thing as 1 minus the probability that none die, right? And if none die, that's also the probability that they all live, right? And we know the probability that they live. Okay? So the probability that they all live is 0.9986 to the 1,000th power, and it's 1 minus that, right? Okay, so complement rule is way quicker and easier to do than to do this 1,000 times. Okay, so that works out to be 0.75364. So there's a 75% chance that at least one person will die of 1,000. That's a little higher than I expected, right? Because they're all supposed to live, because, you know, 24-year-olds jump off cliffs and drive motorcycles and do dumb things. All right, so there you have it. Quiz tomorrow will be on 5.2 and 5.3, and we'll see you all tomorrow.